Okay. Well, I know we're going to go through a lot of material today, so I don't want to take up too much time, but now's a great time to start. Um, Thank you, everyone, for joining us yet again for another week
Happy to.
of discoveries and insights as we continue to explore the theme as above, so as below, reuniting the macrocosm and the microcosm. Many people have realized by now that there are a lot of holes in a lot of the mainstream ways of thinking and narratives that are given to us to use as we penetrate into the mysteries of the atom, into galactic space-time, into so many variables, even of life science, of evolution. And a lot of data is left out of the mix when we're told that we have these tools to now make discoveries. Well, not only is there data left out, but there are a lot of insights of great minds of the past who are withheld. So we're, as much as we have great discoveries and technology occurring, how much greater could it be if this withholding wasn't happening and we actually had access to the full body of real fruitful knowledge that we could internalize into our own worlds, into our own minds, and penetrate ever more deeply into the mysteries of the universe that we ourselves are a part of. So part of the theme of this series has been to not only look at breaking down the barriers separating the objective from the subjective universes, which are two sides of the same coin, because any explorer has to take their own mind into consideration when exploring the world that they're seeking, and also the past and human history. We haven't yet looked at anything regarding ancient history, which today we're privileged to have a good friend of ours here at the Rising Tide Foundation. Cynthia and I have known Stephen now for almost 2 years. Stephen has an incredible biography. I mean, just a couple of the points that we made public on our website here is that he's a retired third-generation Royal Canadian Air Force officer with an expertise in celestial navigation and anti-submarine warfare. More importantly, Stephen is a profound devotee of the truth, and he will look for ideas and truths wherever they have value, anywhere. And he recently brought up to me the issue of Charles Hapgood, who wrote an incredible book in the 1960s, which we're going to look at, which explodes some of the popular mythologies around ancient astronomy and ancient civilizations, and a lot more. So with that, I will give the baton to Stephen, who will grace us with some ideas.
Well, thanks very much, Matt. Thank you, everyone, for indulging me with this. And as I hit the share screen button, and I try to bring up my PowerPoint lecture, how's that look to everyone?
Excellent.
Okay, super. Just a caveat, whatever expertise I did have was circa the 90s, so I had to resurrect a few synaptic pathways in revisiting this, but I think I revived enough that we can get through it. If you're wondering why I have not only the cover of the book we're discussing, but one of C.S. Lewis's books, Narnia, it's because the current lecture series, The Language of Science and Technology, is inadequate to express the impact that Hapgood's book had upon me. And I'd have to almost revert to the previous lecture series and the concept of poetics, and specifically the device of metaphor, to say that Hapgood's maps was my own wardrobe that led me into a magical world of intellectual discovery and exploration. And with the caveat that within that Narnia, there are also things that are a bit frightening and threatening. So as we get into this, there's a wealth of material. If I was a college professor, I could easily make a full credit year-long course out of maps. We'll have to just pare it down to the essential information. Okay, so how do I get my next slide on this dumb computer? Here we go, I'll click on this. And just to double down on that sort of magical, wondrous world thing, I pulled out a famous Sherlock Holmes quote: "When you have eliminated all which is impossible, then whatever remains, however improbable, must be the truth." And we will be getting in there. Some people may have to suspend disbelief for a bit. If my intent with this is to revisit my own Narnia and to bring you with me, I only know one route to that wardrobe and through it, and that's kind of reviewing some of the essentials that brings out the full richness of what Hapgood found. So we'll do a really quick overview of just the essential elements of geography. We'll get a feel for the complexity and scope of cartography and some of the practical aspects of celestial navigation. And we'll do that with kind of a historical framework, just so we can have a good situation with which to appreciate Hapgood. We'll look quickly at the man, what little I could find on him. I apologize in advance. The sources are not the most rigorous, but we'll make do. And then we'll dive into the maps, and we're very much looking at the forest versus the trees in detail, and we'll only select those trees that really bring the full picture to life. And assuming we get through this and we have time, we can discuss Hapgood's thoughts on the implications and possible segues in the field for those who are interested in pursuing further. Okay, so the basics of the geography, the Earth is not a perfect sphere, but for our intents and purposes, it's close enough. I'm sure we all understand north, south, east, and west, but technically it all starts with the Earth's rotational axis and where it intersects the Earth, and the Earth rotates from west to east. In terms of the geometry of a sphere, there's only two definitions, fairly simple, that we need to know. A great circle is a circle on the surface of the sphere or our Earth that has as its center the center of the Earth. So think of the largest possible circle you could fit on the surface of the Earth, or a circle that bisects the Earth into two perfect hemispheres. And a small circle is any circle on the surface of a sphere of the Earth that isn't a great circle. So in terms of the Earth reference systems, we get into parallels of latitude, the north-south stuff, and the meridians of longitude, the east-west stuff. And from my readings, this concept is attributed to Eratosthenes. So I think we're talking circa 250 to 200 BC. But basically, if you look at this diagram, the equator is that great circle on the surface of the Earth whose plane is perpendicular to the axis of rotation. And then all the small circles whose planes are parallel to the equatorial plane are the parallels of latitude. And for east-west, the meridians of longitude, these are defined as the semi-great circles that connect both poles. So back to the parallels of latitude, the equator stands out as unique amongst the parallels because it's the only great circle. So that's the obvious start of our reference system. But for the east-west meridians of longitude, they're all exactly the same geometrically, so none of them stand out, and we have to arbitrarily select one, and it's been designated the Greenwich meridian as the prime meridian. So as opposed to an XY grid reference system, at right angles, on the sphere we're using two angles that are whose planes are at right angles in essence. So if X is the spot on either of these globes that we're interested in, to measure the latitude, we'd measure along the local meridian. We'd start at the equator, go to the center of the Earth, and then go to the spot on the meridian. So in this case, it's 30 degrees north latitude, and if it was symmetrically on the other side, it'd be 30 degrees south latitude. So to measure the longitude, we would go down the local meridian to the equator, and then measure from our reference meridian to the center of the Earth, and then to that meridian. And east-west is measured in degrees, longitude is measured in degrees east-west up to 180 degrees. And there are two pairs of parallels of latitude that are not numerically defined, but they're astronomically defined, and they do come up in Hapgood. So we'll just take a quick look at the tropics and the Arctic and Antarctic circles. So this dotted horizontal line represents the path of the Earth's orbit around the sun. And as we can see, the Earth's axis of rotation is actually tilted with respect to that orbital plane, if you will. Just a little bit of trivia. That's about 23 degrees and change. It fluctuates over a 41,000 year cycle, the obliquity cycle, plus or minus 1.1 degrees. The actual numbers are not important, it's just the concept. But if you look at, where's my cursor here? This Tropic of Cancer at the June solstice, and you're right here, this is noon local mean time because the sun is directly overhead your meridian. And this sun would be like literally overhead 90 degrees straight up. And this happens everywhere on the tropic because you're rotating to this point in essence. And then the same thing happens on the December solstice in the southern hemisphere on the Tropic of Capricorn. The sun is 90 degrees overhead, and you rotate into this position anywhere in the tropics. So the tropics are really the northernmost and southernmost boundaries where the sun can literally appear 90 degrees overhead at local noontime. Numerically, they're about 23 degrees north or south, but again, that'll fluctuate as the obliquity angle fluctuates over time. Okay, there's my cursor. Now, if we also look at the polar regions during the solstices, and you have to remember that the solstices, the axis is most pointed directly towards or away from the sun. If you're on this, oh gosh, I keep losing my cursor here. If you're in this little spot here, you're actually on the night side of the Earth because the sun is directly overhead your anti-meridian. So you're on the cusp of daylight and sunlight here, but then you rotate back into sunlight. So this is the southernmost extent of 24-hour sunlight. And the opposite happens in the northern polar region at the December solstice, that you're just on this cusp, you rotate back, so you're 24-hour darkness. And the same thing happens in the Antarctic circle. It's just that the reversed June and December solstices. And for scale, this is a modern map showing the South Pole and Antarctica. And this dotted line here is the Antarctic circle, and it's roughly 66.5 degrees south latitude. Okay, so that's all the geography we need to understand. And remember, in terms of getting a grasp of what cartography is all about, we're in essence trying to go from the Earth sphere to the plane of a flat map. So you can either have the whole world or most often a portion of it, and we mathematically place it on, in our case, not a spheroid, but a spherical georeference construct, but we have to mathematically project that onto a flat map surface. And as a corollary of Gauss's theorem egregium, I hope I'm pronouncing that correctly, it is mathematically impossible with the certainty of mathematical proof that you can do this without distortion. Although common sense says that if you took an X-Acto knife, and peeled apart the outer layer of your office globe and spread it out flat on the desktop, you'd recognize that it was the surface of the Earth. But in terms of having any rigor or mathematical consistency, you've destroyed that and introduced distortion. But if we could make a perfect map, it would have the following desirable properties. So it would have conformality. So we measure an angle on your map, and it would correspond to the exact angle on the surface of the Earth. It would have constant and correct scale throughout. I've worked with maps that don't have that, but there are plotting techniques that you can get around it. It would have correct shape representation or orthomorphism. What you see on the map would correspond pretty much to what you'd see in orbit above that point, for example. But that isn't always the case. You would have correct area representation, and I will show you examples where that isn't always the case. It would show a great circle with a straight line, which is an advantage because on the surface of a sphere or the surface of the Earth, the shortest path between 2 points is actually the great circle path between them. And let me see if I can find my cursor again. The last one, it doesn't get into a lot in Hapgood, but it's a main property. A rhumb line would be shown as a straight line. And this is actually a good illustration into, if you don't know what you're looking at, things that seem to be radically different actually are quite the same or the opposite. But if you look at this curved line here and this curved line here from London to New York and from Madrid to New York, these are the exact same lines on this map, but because they're different projections, they look very different. So a rhumb line is a concave line on the surface of the Earth, sorry, concave to the nearer pole that cuts the meridians of longitude at the same angle. So the advantage to traveling a rhumb line track is it's a constant heading track, so it's easier to steer even though it's not the shortest direct path between 2 points. And I guess the point here from this example, or two of them actually, first of all, you have to be very careful. You have to understand the projection you're dealing with because you could be dealing with visual distortions. If you're not aware of it, you might make errors in using the map. And the other thing is, if you're the cartographer or the navigator, you want to select the projection type that preserves what's critical for your intended use and know and accept the fact that you'll have distortion in other areas. So if we look at that left map with the straight rhumb lines, that was the famous Mercator projection. And that's of the category or class called cylindrical projections. So, and I'm going to show you just three of these main classes, the more common ones, just so we kind of understand just how complex and how these things go about. This, where's my cursor again? This is a two-dimensional representation of a three-dimensional geometric figure. So it's an intellectual construct, if you will. But you can think of it as a glass globe with a light in the center, and you have a paper rolled up in a cylinder. You project onto the paper, trace it, unfold it, and here's your map. That's not actually how they're made. That's just understanding the concept. So if you look at this cylindrical projection, first of all, it's obvious there's a weakness. You can never represent the two poles, for example, because the cylindrical axis is parallel to the Earth's rotational axis. And if you think about how your shadow gets longer as the sun's starting to set, because you have a lower and lower sun angle, you have a similar distortion as you get the higher and higher latitudes, things stretch out. So in this standard cylindrical projection, for example, you get more distortion the further north or south you go. So this is probably what we all remember from our middle school chart on the wall, map of the world, with this big honking Greenland here. And I pulled up this image from the internet showing aerial distortion of different map projections. So this is the map Mercator. So it superimposes Greenland and Africa, Greenland and green, and they look roughly the same size, but we know there's some distortion here. And if you go to these two projections, sinusoidal and mollified, these two projections preserve relative area, and they show the correct relative area ratio of about 13.9 to 1. So again, we have to keep in mind that if the medieval cartographer have access to ancient maps that are actually based on differing valid projections and they don't understand this, they might be dealing with apples and oranges and actually trying to mix them together, combining maps. There's another thought too. The cylinder doesn't have to be vertically oriented. It can be horizontally oriented for transverse cylinder, or it can go on an angle here for an oblique cylinder too. So when you look at all the variations on a theme, they can be quite numerous. You can also shrink the cylinder so it intersects the Earth too. But in terms of this being tangent at the equator, there's very little distortion at or near the equator. So this would be an excellent projection type to use for navigation in the tropics, for example. And next slide. Next category are the conical projections. So let's say that I didn't want to navigate in the tropics. I wanted to go a little higher north or south. These types of projections might be a good one to use. And it's basically putting a Dixie cup over the North or South Pole, or you could do it anywhere else, for example. And again, you can do it tangentially or secant. But you can come up with something like this, for example. And I've actually flown with a Lambert conformal conic map, good for continental US, bottom third of Canada if you're in the Northern Hemisphere. I found this variation on the theme that used different cone geometry for different latitudes, come out like this. Apparently this one's not used anymore, but it illustrates that you can have different geometries and different variations on a theme. And the third major category that I want to talk about, and in my experience, these are the ones you tend to associate with the polar regions, are the azimuthal projections. So instead of projecting onto a folded plane in the terms of a cylinder or cone, you just project onto the plane itself. So the orthographic, you have the disk of the equator as the projection plane, all parallel, and you get this. I have not used that. I've used the stereographic ones, polar stereograph. And if your plane is tangent at the North Pole, the projection point is at the opposite pole. You can see this distorts the area size of the southern continents vis-a-vis the northern continents. Okay, so I've used this, but the rule of thumb I was taught is we tend to use those above 60 north. And of course, we were in the south, it would be 60 south. And the mnemonic, and I had Navy friends said that they had these, but they rarely used them. And that way your projection point is the center of the Earth. And just as a point of reference, Thales apparently introduced this in the 6th century BC, just for reference. One more slide on the maps, cartography. In my readings, I've learned that there are over 1,000 projection schemes that have been developed, mathematically rigorous. And from one webpage that I found with over 100 different world map projections, I just pulled these ones out because I learned something. This Robinson guy, instead of saying that I should preserve some of these desirable properties, it says that I don't want to have great distortion in any, so I'll accept small distortion in all. So it's kind of a hybrid or compromise map. But even then, it does a terrible job of representing Antarctica. Even worse are these two projections. And it takes this weird polyconic projection to actually have a reasonable depiction of Antarctica. So again, there's so many ways to skin a cat on this. And if you don't know what you're doing, or you're in an epoch of time where you haven't had this sort of mathematical knowledge developed and the field developed, you can get into some basic problems trying to glue together certain maps if you're making a composite map. Okay, now navigation. So celestial navigation, astronavigation, You can use it for position lines, heading checks, or calculations of rising, setting, and twilight. And the bodies that you use are stars, sun and the moon, and the planets visible with the naked eye. I pulled some pictures out of classical nautical sextants, and sextants are devices that are used to measure the angular separation between two heavenly bodies. But in my experience, they're mostly used with the horizon and one body in the vertical. And that's the sort of one that I use, I'll get into. But if you look at this device here, and let me just see if I can get rid of, yeah, that's blocking my screen. Conceptually, I pull this off of Wikipedia, you have a telescope, and we can think of this as a one-way mirror so that you can orient against the horizon to level your device, and then your measurements have meaning. And then this moving pendulum type arm on the scale is attached to the upper mirror, and the sun's up here that you want to shoot. So you would move the cursor, you'd move this device back and forth to adjust the angle here so that the sunlight would bounce, and you'd see kind of this picture. And that would give you the angular height or altitude above the horizon in terms of your celestial measurement. And a little tidbit, because I've actually done this, the stars and the planets are point sources, so it's relatively easy to center them on kind of your crosshair point. But the sun and the moon are a bit too large, and that you can introduce navigator error trying to figure out where the actual center is. So it's a lot easier for the human eye to get the bottom or top tangent point, and then you just apply a small tabular correction to do that. And the other thing that might not be obvious when you look at the nautical sextant is that you need to actually be able to see the horizon to take your measurements. And for that, you need light. But if you're shooting the stars and the planets, you need dark. And the only time you get the two of them in the right combination are at morning or evening twilight. So in terms of doing fixing with those bodies, you're kind of constrained in the nautical environment. But the plus side, you're only going, what, 6 knots, 6 nautical miles an hour. So you don't need to fix that off and crossing the ocean. On this aeronautical one, I'm kind of like the German submarine commander in the World War II movie. This thing actually sticks up out of the aircraft like a periscope. I can't see the horizon because I'm in a tin can. So what the designers of this thing did is within the optical path, they put a little cavity with a clear viscous fluid and a gas bubble in it. So basically there was a carpenter's level bubble in my field of sight that acted as an artificial horizon. And depending on whose claim you believe and how you want to date this, this technology in the nautical environment dates back early to mid 1700s. And a lot of what you need to determine, especially longitude at sea, traces back to that century. So in terms of the theory, and let's pretend we're kind of in the age of sail here, we take Copernicus and all his great advances and we throw him overboard. Honest to God. And what I was taught was it's almost the old observable astronomy. Conceptually, it's what you perceive as a person on the Earth. So we imagine that there is a celestial sphere of infinite radius that's concentric with the Earth, same center. And instead of the Earth turning from west to east, it's the celestial sphere turning in the opposite direction. And because these are all stars are all fixed relative to one another, so Orion's belt was the same way 2,000 years ago from our perspective, and it'll be that way 2,000 years hence, hopefully. In the same way that a geographer can build up a catalog of latitudes and longitudes on Earth, the astronomers can build up a similar catalog of the celestial latitudes or longitudes of the stars. And conceptually, we were taught that the moon doesn't fit this pattern because its apparent motion is not primarily due to the rotation of the Earth. If we look at that sort of celestial frame reference system that's analogous to the Earth latitude and longitude, on the celestial sphere, we have celestial poles. I was taught that instead of an equator, we have the equinoctial, but it's a celestial equator. It probably makes more sense. Instead of latitude, we have declination. Exact same thing, degrees north or south of the celestial equator. We had to pick the Greenwich meridian as our reference for longitude. What we do in the celestial sphere is we project the vernal equinox out onto it, and it has the added advantage of also being on the celestial equator, but it defines our reference celestial meridian. And this is also referred to as the first point of Aries, or just Aries. Instead of longitude, we have something called the sidereal hour angle, but it's essentially the same thing, only it's measured westward through 360 instead of going 180 degrees east or west. Essentially the same thing. And my own take on why it's called an hour angle, if you look at locking the Earth and the celestial frames of reference, you have a fixed rotation rate. So 360 degrees in 24 hours makes for 15 degrees an hour. So time and angle in terms of east-west type thinking or westward through 360 are perfect natural proxies for one another. I wrote Earth's orbit here because that's how I think of it, but technically it's supposed to be the apparent annual path of the sun as viewed from Earth, but that's defined as the ecliptic, and that's the red great circle here. So in essence, for a celestial reference system for all the stars, let's say, you have declination, you have this sidereal hour angle, which is the analogy to longitude, and you try to lock the two systems via something called the Greenwich hour angle of Aries. So vernal equinox, first point of Aries, or just Aries. And the Greenwich hour angle is basically the difference between where the Greenwich meridian is aligned at any given time and your reference celestial meridian. So if you think back and you're the early astronomer royal at the Royal Observatory in Greenwich, you have your state-of-the-art pendulum clock and you're about to start all the system up, you have the ability via observation to say when the sun is directly overhead your local meridian. And you say, okay, it's noon. You wait for it to happen the next day, and maybe your clock's a little off, so you tweak it a little bit until you perfectly synchronize your pendulum clock to that sun going over the local meridian, and now you know your Greenwich clock is bang on. And the next thing you do is you look out there and you say, okay, I know where the vernal equinox is in the sky, and via celestial observation, I know when it's over my local meridian. And you note the time, and then you've got sort of a plot log between terrestrial and celestial, because that difference, that Greenwich hour angle of Aries, GHA of Aries, off the overhead time varies by 15 degrees an hour. It's just a constant. So it's pretty easy to come up with this once you have the clock technology and the observational technology. So in terms of the data, the Greenwich hour angle, the declination, the sidereal hour angles, all that sort of stuff, these are published in almanacs and related pubs. And very quickly, the Royal Observatory was commissioned in 1675 explicitly to determine longitude of places and to improve navigation. They published the first almanac 1767 under the 5th Astronomer Royal Masculine. And I'll get into lunar distances in a bit. 1832, that function is transferred to Her Majesty's Nautical Almanac Office. The US Naval Observatory starts doing this in 1852. And for the Quigley fans, Royal Navy and the US Navy started jointly publishing in 58. I use the US Naval Observatory Air Almanac and associated pubs, and that stuff is still available online. And just an aside, I pulled this image off the internet. I've actually seen this done in the nautical context once with some naval colleagues, and for them it was actually a two-person evolution. One to do and one to record, whereas in my game, it was a one-man operation. So this is what an almanac would look like. I don't want to get into great detail, but here you have universal time or Greenwich Mean Time. There's the GHA of Aries. So there's the way to plot lock between terrestrial and celestial, because the actual mechanics of the planets are a little different. They have all the information there. There's the stars, sidereal angle, declination. There's more information. You can do moonrise, sunrise, twilight calculations from here. But if you notice, this is valid for 3 days. And this hadn't occurred to me before, but if there are minor differences between any 2 days, if you publish for every third day, you've eliminated 2/3 of the work. Because we have to remember, this is pre-computer, but post-Napier. So we're dealing in the age of slide rules. And for the astronomers crunching out these numbers and almanacs, it's a lot of work. So for them to do that every 3 days cuts down a significant amount of paper and computation. Okay, so how I actually employed this was something called the Mark St. Hilaire method. And remembering that we're in the age of slide rules starting off, we're in the age of tables. Any navigator worth their salt should have some idea where they are roughly. And to go into these tables to shoot a position line off that star, and there's your ground position for the time, I would choose a position near where I thought it would be that was sort of a whole fraction of latitude and longitude, so that it allowed for easy entry into the tables, because it's not like this stuff evolved in the days of iPhones with enough computing powers to crunch numbers for any spot on Earth. So I would have an assumed position, and I would extract the true azimuth to look for the star. So that'd be where to orient in the horizontal to point my sextant, and then the angular height or altitude calculated that I would look up at that azimuth bearing to find the star. Only I know I'm probably not there, I'm close to there. So I actually, in this case, I would have shot this angular height or altitude that I actually observed. And because the angle, let me get my cursor again, because the angle is smaller than I was anticipating, I know I have to be farther away just from the geometry. And in theory, I'm anywhere on this kind of range circle that would have that angle if, you kind of rotated that line around this vertical line to the ground position. Now, I'm most likely here. And what I was taught is that's not quite good enough. It could be errors or inaccuracies. So we'll draw a tangent line here, line of position. And in theory, I'm somewhere on that line. And the angular divergence here is so small that I'm not going to worry about it. But in an ideal world, I'd have at least a second body at a right angle, and I'd have a right angle cross for a second position line just to confirm it using the same process, or even better, a 3-star fix, roughly 120 degrees apart, and I have 3 position lines intersecting there. And then with your standard geometry kit type tools, I would extract the lat and long off the map or chart. So that is kind of how the navigational process and methodology evolved. And that's indeed what I was taught in basic navigator trading. What else? So if this is the pole star, and I confirmed this one in my research, this actual observed height is your latitude. So finding latitude is not that difficult. And also if you have declination tables, there's a way of determining it via shooting the sun when it crosses your meridian. This is just the geometry of if this is Polaris, this is your actual latitude. But if you think back to Eratosthenes and the conceptual birth, as we understand it, of latitude and longitude, as we're about to discover, it's about a 2,000-year process in terms of human advancements until we can accurately measure longitude at sea. So it's different at sea than at land. So some of the methods they developed for determining longitude in the land just wouldn't work at sea. 2 different observatories observing the same eclipse, for example, or there's a technique that was developed with observational astronomy with the Galilean moons of Jupiter. So it's just not practical at sea, and no one can actually measure longitude at sea. Spain tried in the 1500s to wave a carrot, no luck. Holland tried in the early 1700s, no luck. And it took a Royal Navy silly disaster of 1707 to really light the fire under the only entity with the resources and the desire to do that, and that was the naval empire of Britain. And good Sir Cloudesley Shovel, and here's a real Horatio Hornblower sort of guy, along with 4 of his ships, grounded and sank when they struck the Isles of Scilly, which was attributed to a navigation error. Supposedly, somewhere between 1,400 to 2,000 people lost their lives in that disaster. So I don't know if the Royal Navy was particularly bad at crew manifests, or they think up to 600 sailors swam to shore and ran away. But not being ones to waste a good disaster, if you can pardon the expression, they memorialized Shovel in Westminster Abbey with this, and eventually they get funding for a board of longitude whose mandate is to crack this puzzle of how do we determine longitude at sea. And because they had funding, and not only were there rewards for devising methods to determine longitude at sea to certain degrees of accuracy, they had seed funding for promising ideas. So they're almost like a 18th century Royal Navy equivalent to the CIA's In-Q-Tel venture capitalist arm. Kind of interesting, but eventually that got it done. And there were 2 main methods that competed in the 1700s for this prize and to become the dominant method of doing it. So, and I liken it to VHS versus beta war. And without getting into too much details, because this is a rich story unto itself, you have what I was taught, and it's sort of a time predicated approach to it. Where's my cursor? There we go. So clockmaker John Harrison says, I'm going to crack this nut. Starts around 1730 with its first version of a maritime chronometer, because under this approach, the big impediment is you don't have an accurate clock that works at sea, because pendulum clocks don't work at sea. So he does model H1, H2, H3. H4 was the one that met the criterion. Very expensive starting off. The technology got cheaper later, and so on and so forth. Kind of a very interesting story. A superior method around the 1750s arise via the method of lunar distances. And I pulled this off the Australian National Museum website. It has to do with more precise, more sophisticated angular measurement. But this one, because it requires precision, you had to have an achromatic lens, or one that corrects for chromatic aberration. And very simply, you know, when we're in our basic science class, we're taught that, here's my cursor, lenses have an index of refraction. That's a simplification. That index of refraction varies as a function of wavelength. So instead of one focal point, you get a bunch of different focal points for the different wavelengths or colors. So the achromatic lens corrects that. And to summarize this very quickly, from my readings, both methods were valid, both were used, but about the 1850s, this became the dominant method. So and that's what I was taught, the time-based sort of method. This is something I pulled from popular culture, and it was just to kind of throw an idea out for the gang. Within this game civilization, which has legitimate pedagogic value, you're trying to grow your little tribe into the dominant civilization, futuristic civilization on the planet, and it records all the great progressive milestones in various disciplines, whether they're intellectual, technological, social, cultural, and it kind of maps them out, and you have to have certain ones before you can move on to the next one. So even though I found that this thing didn't actually jive with my research on navigation and clocks, all that, you know, if you try to apply it, I mean, and you think about the challenge of determining longitude at sea, and eventually Harrison's sea clock that allowed it, or the method of lunar distances, I mean, your civilization would have to have astronomy, have to develop navigation, probably magnetism and compasses, so that you have longer range voyages. For the astronomy, you may need physics, you know, Newton's sort of stuff, or optics for the achromatic lens. If you're doing almanacs, you need a printing press. Certainly with your observatory, you need clockworks. And then later on, when you're in a larger maritime empire and you've got shipbuilding and tactics and strategy, really you may have the driver to take clockworks for the sea clock. So, and I'm not suggesting we apply this. I mean, I don't want to insult anyone. It's just that the concept, when you think about determining longitude at sea, it was a most vexing problem. And it took the better part of 2,000 years to sort that out. Okay, so let me get the next slide. Again, apologies for the lack of rigor in these sources. It's the best I could come up with, so take it with a grain of salt. When I looked at Hapgood's parents, and the family papers are held by Yale, Father Hutchins Hapgood, undergrad and master's at Harvard, journalist, anarchist, and a feminist or a feminist supporter. Mother, maiden name Neith Boyce, novelist, journalist, theater, and apparently the two enjoyed a bohemian, open, and free love marriage. Kind of interesting. And I found that via a Wikipedia reference, and it's a defunct online anarchist encyclopedia of all things. So again, we'll take this with a grain of salt, but apparently the father had a tremendous influence on the character of his sons. Although not religious, he imparted to them a strong moral sense, abhorrence of great wealth, and a basic belief in progressive socialism. This, coupled with a liberal Harvard education and appropriate connections, led Hutchins Hapgood into the thick of mudraking journalism. Elsewhere, I also read that he'd spent some time in Germany and Japan, which, you know, given the rough time frame, makes me open to the possibility that there may have been an intelligence connection to the family. Not necessarily, I wouldn't discount it. But also during the final years of their lives, Hutchins and Neith worked on a project which aimed to relate the story of the Hapgood family to the history of the US, so 1648 to 1917. The parents acquired copies of significant correspondence, most notably that between Norman Hapgood, Hutchins' older brother, or Charles Hapgood's uncle, and Supreme Court Justices Louis Brandeis and Felix Frankfurter, another distinguished journalist, Judge, Learned Hand, and Presidents Woodrow Wilson and FDR. The folder of Teddy Roosevelt's correspondence reflects the relationship between the president and Colonel Henry H. Boyce, niece father. So I can't say for certain, but it seems like these two were reasonably well connected and kind of an establishment couple, even though they're portrayed as being very anti-establishment. And whether that's actually true or whether that's something someone wants us to believe, I don't know. In terms of Charles Hapgood himself, again, this is Wikipedia or Wikipedia references. So take this with a grain of salt. Like his father, undergrad masters at Harvard, and that was supposedly medieval history. He completed his PhD work at Cambridge. And for some reason, I'm thinking Kim Philby maybe, but who knows, in history. And it was associated with the French Revolution. But Hapgood didn't finish his dissertation. And it's kind of alluded to in my readings that this was because it was in the height of the Great Depression. But I suspect that it might be another reason, which I'll get into in a bit. He supposedly was the executive secretary of Franklin Roosevelt's Crafts Commission. In World War II, he was employed by the Office of the Coordinator of Information, which became the Office of Strategic Services in 1942, which I believe became the Central Intelligence Agency after the war. So we're seeing an intelligence side to Hapgood, which given his history background is understandable. And also the Red Cross, what a great way to get intelligence in places that you can't send soldiers, for example. And he also served as a liaison officer between the White House and the Office of the Secretary of War. So Hapgood must have had a pretty darn good bird's eye view at a strategic level of what was going on during the Second World War. We know he corresponded with Albert Einstein on Earth crust displacement theory. And while Hapgood didn't originate it, he was one of the early proponents of it. He certainly was the first one to popularize it in terms of publishing a book accessible to the general public. And after World War II, he taught at the college level because he doesn't have his doctorate. And we're interested in the Keene State College period, 56 to 66, because in 58, Hapgood publishes his first book on this Earth crust displacement theory. And that basically says that if you imagine the Earth's axis of rotation remaining constant, the outer lithosphere or crust of the Earth can shift so that you get a new North Pole and a new South Pole. And basically all the latitudes and longitudes have to be recalculated and redrawn. And he was struck by a car and died in December 82. So that's all I found on Hapgood. Hopefully it's good enough to add. And now let's walk through the wardrobe. This is the surviving fragment of the Piri Reis map. So it's missing the eastern portion and the northern portion. It was discovered or rediscovered in an imperial palace in Istanbul in 1929. It was made by the Ottoman Admiral Piri Reis. So Piri is the Turkish word for admiral, as I understand it, in 1513. So that was when it was made. According to Hapgood, it displays South America and Africa in the correct relative longitudes, which in and of itself is quite amazing because that shouldn't have been able to happen until the late 1700s. Even more shocking is it shows Antarctica, although it supposedly shows it connected to South America. So now, according to Piri Reis's own margin notes, the western portion was based on a map of Columbus's. It might have been from one of his navigators who was captured. But the overall original map, according to Reis, was built from over 20 other source maps, some dating back to Alexander the Great, not exactly standard academic notation, but we'll live with that, and some of which were based on mathematics. So now with what we know about cartography, this is potentially a bit of a Frankenstein map, because if Piri Reis didn't understand the underlying mathematics, assuming there were some of the source maps, what he puts together could be a real dog's breakfast in terms of mathematical rigor. So anyhow, this stuff kind of gets in the news. U.S. Secretary of State Henry Stimson gets interested. By that interest, U.S. Library of Congress gets a copy, but a second copy comes into the U.S. Nautical, I think that's Hydrologic Office, to the cartographer Walters via a visiting Turkish naval officer as a gift. He hands it off to this Captain Mallory fellow, who's one of these Antarctic explorers, archaeologist, ancient maps sort of guys. Mallory assesses it and says, yep, I'm thinking that is indeed the coast of Antarctica. He does a radio interview. Hapgood either hears the interview or reads the transcript. By this time, Hapgood's already published his Earth crust displacement book. So obviously ancient maps, which might support that Earth crust displacement thesis, would be of interest to him. So he wants to get his students on this and tackling the question of whether or not that's Antarctica. So I did find this article online from the US Naval Institute proceedings from November 61 on Mallory and his claims, but I couldn't get past the paywall. And what's kind of interesting is when Hapgood introduces his book, he extols, and he's describing how this history happened, and he's giving it to his students. He extols the virtues of amateurs because in Hapgood's view, experts suffer potentially from a bias in that their thinking is limited by the scope of their great knowledge of the existing body of knowledge. And experts, according to Hapgood, tend to look down on amateurs when in fact amateurs have made many of the major discoveries in science. And I'm almost wondering if that doesn't relate back to his PhD thesis and dissertation and not doing it. I'm wondering if he had too radical of an idea that wouldn't be accepted by his thesis advisor or the whatever board he'd have to go in front of. So I don't know this, that's speculation, but Hapgood is very, very big on amateurs, and he really let his students run with this. So it was kind of refreshing to see. So as Hapgood is starting this with the students, he's also looking out to see what sort of the state of the knowledge in the field is. And he comes across an expert, a scholar by the name of Nordenskjold, who had compiled an atlas of 14th to 16th century maps called portolans, from the Portuguese word portolano, port to port. So these are a series of maps that are all essentially similar and tend to be focused on the Mediterranean and perhaps the Black Sea. But Nordenskjold determined that this set of maps had to have ancient origins because they were superior cartographically, mathematically, to the rediscovered maps of Ptolemy. And because they were all similar, Nordenskjold felt that they were all from the same original source map that was kind of lost to history, which he called the normal portolan. Now, the portolans kind of varied in rigor or accuracy. So I guess some of them could be copies of copies of copies, whereas some might have been the copy of the original. So anyhow, Hapgood now knows that there is a tradition of in high antiquity, the possibility that there was some really accurate map knowledge. So they're going through their laborious trial and error effort to reverse engineer Piri Reis, because they're literally doing an autopsy on a Frankenstein map, and they're trying to pull the different body parts out, if you will, and determine which ones relate and where they came from, where the bodies were buried. It took them 3 years of this very difficult pre-computer, all by hand effort to determine that the mathematical center was Tropic of Cancer and the Meridian of Alexandria, which is kind of interesting. And when they're doing this and they're trying to put modern grids or projections onto the maps or different parts of the map, they had to make certain assumptions, and if the assumptions weren't right, they had to redo them with different assumptions. But he did find evidence of plane and spherical trigonometry, which is interesting. And he found evidence that the cartographers of Alexandria, because we know from Piri Reis's own notes that some of the maps came from there, themselves had ancient maps that did not reflect Eratosthenean, if I'm pronouncing that right, error in the Earth's circumference. And so when you're reading this and all the gory details of the trial and error, one of the things they had to do at some point is to assume a certain circumference on the part of the cartographers making the sections of the map. And when they use the Eratosthenean error or values, they couldn't get it to fit, but the errors minimized and almost disappeared when they used the actual value of the Earth's circumference. So there's some interesting stuff going on here. They're finding evidence that there's more advanced ancient technology and knowledge than history records. Some other anomalies, the Amazon River is represented twice. So again, if you're Reis and you have a bunch of maps and you don't understand the projections that they may have been based on and how that would distort what you see, you could have two maps that you're trying to glue together and not realizing that on each map you're showing the same river. For example, the Caribbean Islands were out of orientation. Some other maps that Hapgood's found suggested that someone had mapped the St. Lawrence before Columbus officially discovered the New World. So right then and there, we're introduced to the possibility that all of these early explorers and discoverers of the New World were in fact following old maps and just confirming that they were actually accurate. One of the students pointed out you could also possibly infer the Andes Mountains in South America, which means that someone had to be viewing it from the West Coast versus the East Coast. When we get into the Antarctica question of the Piri-Reis map, from one of my readings, Antarctica was first sighted in 1820. It's contentious, but they found the same thing as Mallory, although the Drake Passage between South America and Antarctica is omitted. Hapgood notes that Mercator and other cartographers of his time believed in the existence of a southern continent, which again suggests that they had access to older or even ancient maps that depicted it. And this belief existed in the field until Captain Cook failed to discover it. And, you know, if I put my tinfoil hat on, I almost wonder if that wasn't part of Cook's purpose, but, you know, that's pure speculation. But according to Hapgood, Queen Maud's Land's rugged coast, which is part of Antarctica, the Piri-Reis map depicts without ice with good seismic correlation to the then known data. And as he points out, further confirmation comes from other maps predating Antarctica's official discovery. So then he jumps to the Orontius Phineas map of 1531. And just looking at it, my gut tells me it's based on rigorous spherical trigonometry. It looks like a legitimate projection. And it's a beautiful map, but it depicts Antarctica as way too large. And Hapgood found this in the previous map and in other maps that depict Antarctica inexplicably. And he found an explanation for it. If there had been some ancient source map that had the 80th parallel, but without explicitly designating it, the map maker may have mistakenly assumed it was the Antarctic Circle. So, and if you look down here, so if you can imagine, if the ancient map had that circle without annotation and it didn't show the Antarctic Circle, the medieval cartographer might think that's the Antarctic Circle and blow up Antarctica. And you can see here, it's also showing surface features, which means whenever this was made or whatever the origin was, it had to have at least been ice-free around the coasts for you to sail around and see this stuff. So it may or may not have been partially ice-covered in the center. But Hapgood points out that the knowledge at the time says that Antarctica, the last warm period ended 6,000 years ago by virtue of the raw sea cords from the 49 bird expedition. And he also notes that, you know, the nature of the errors he found suggests that it was actually based on a composite map or other maps glued together. But if we blow that up, he also notes that the south pole of Orontius Phineas is a little off from the modern version. And so this kind of gets into Hapgood's idea that the poles can shift over time to varying degrees. And one thing I found reading maps is you can't divorce maps completely from Hapgood's work on Earth crust displacement theory, because the two are intrinsically linked. It gets worse. So we've already seen evidence of a cartographic tradition that should have late 1700s level technology and knowledge that it's probably going back at least 6,000 years. In the Haji Ahmed map of 1559, it appears to exhibit highly sophisticated spherical projection. But if you look in red here, Hapgood says there's the suggestion of a land bridge connecting Alaska and Siberia. And he goes on to say, lest the reader read these words in horror, this is but another link in the chain. This implies you're going back into the last ice age. And Hapgood understands just how radically significant that possibility is. And I just threw that little submarine there because as opposed to thinking of a link in a chain, when I hunted these little rascals, they're under the water, they're invisible, and it's not like a video game where you either know it's there or not. Sometimes you'll have a sensor giving you some evidence, but you might have a low confidence, or over time you might see an evolution of events or facts or other sensors coming in that builds it. So we refer to it as cumulative evidence, and you wanted to have enough cumulative evidence that you were at a certain degree of confidence you were dealing with a sub. And from that, we're thinking, I am seeing Hapgood building a body of cumulative evidence pointing to something significant happening in high antiquity. And just for reference, I found this modern scientific paper that says that there's credible scientific evidence that the inundation of the Bering land bridge or Beringia happened 11,000 years before present. So this map, while not definitive, certainly does suggest that it could go back past that date. So we take a breather from the really high drama and we get back to just moderate drama. in this map, the Ronell chart, 1510, Hapgood analyzed it and says that it displays more geographical information that history says was available to the Portuguese in the first decade of the 16th century. So Hapgood, and it's not a great representation. I'm sorry, I took a photo from my book. But he says it shows a coast of Australia. It shows a better knowledge of longitude than that could reasonably be expected. And Hapgood's inference is there was an unknown source map of magnificent origin, adulterated over time by medieval cartographers ignorant of the original projection. And so we see the problem if humanity loses the knowledge that was there in the ancient past, the mathematical projection, then you have a medieval cartographer trying to rebuild this or reuse it. They can actually screw the map up through ignorance. Hapgood tries to go further east, no luck in Japan. He hits pay dirt in China via a 12th century map that's actually carved in stone. I just pulled that off of Wikipedia. That's the UG2 map dating from 1137, the Stele Forest of Xi'an, Jiangxi, China. But as Hapgood points out, that's when they carved it into stone. No one knows the antiquity of the original map or data that were used to carve into the stone. The river system show remarkable correlation with modern maps, excellent info as to longitudes. As with Piri Reis, there's evidence of spherical trigonometry. And along my concept of increasing cumulative evidence, it's at this point in the book that Hapgood says we're probably looking at evidence of a lost worldwide civilization that accurately mapped the world, basically. It gets a little more shocking. When Hapgood goes to the maps of the north, the first thing that he looks at of significance is the Zeno map of 1380, made by Venetians Niccolo and Antonio Zeno, supposedly because by virtue of their voyage to Iceland and Greenland. Now, Hapgood wondered if he didn't see some of Nova Scotia in there too. And he also sees a lot more than just Iceland and Greenland, which makes him suspicious. This map was apparently rediscovered amongst family papers 200 years later by a descendant, and Zenos were supposedly an important family. But when Hapgood put a modern polar projector, so that's one of the projections, that's one of these azimuthal type projections, superimposed on the map, it shows latitude and longitudes were amazingly correct. So another one of these maps is just way too accurate, supposedly for the level of technology at the time. And the other thing he keys in on is Greenland is shown with accurate topological features and shown as being essentially ice-free. So that Captain Mallory is credited as being the first to identify that. And Hapgood, with his knowledge of history, is wondering if the real source of this information wasn't an ancient map that was picked up via the Fourth Crusade. But in terms of that, the implications of Greenland being shown ice-free with accurate surface features. I pulled this up from a modern website, but if you look back at sort of the climate record for the past 450,000 years, we have cycles of glacial and interglacial periods. And very roughly, the glacial periods dominate, so ice ages, and they're on average 70 to 90,000 years in duration. And those periods in between, the warmer periods, are on average 10,000 years. And these warmer interglacials, we're actually in one right now, and we're 11,000 years into it, so we're getting due for an ice age. And if you were looking for the nearest candidate in terms of time when Greenland was ice-free, I found this modern science climate study that says that Greenland was entirely ice-free at some point in the past 1.25 million years, but you would likely go back to the last interglacial to figure out when that would be. But that is, if we look up here, it's on the order of 116,000 years ago, according to this paper. So the other possibility, if you just can't wrap your mind around the fact that there might have been at least a somewhat advanced civilization over 100,000 years ago, you have to accept the concept of Earth crust displacement. And under that, Greenland would have been further south and Antarctica would have been further north, and an Earth crust displacement basically moved the whole surface of the Earth, the whole crust, and it pushed Greenland far enough north that it became glaciated. So it's almost like you have to pick your Hapgood poison. If you don't accept the Earth crust displacement thesis, you have to go back logically 116,000 years before present before it makes sense that Greenland might be ice-free. And if you can't do that, then you have to accept the Earth crust displacement thesis that maybe 20,000 years ago, the Earth crust shifted. So you get into some pretty stunning implications when you start looking at this. Ptolemaic map of the North, rediscovered in the 15th century. Ptolemy pays tribute to Marinus of Tyre in terms of the underlying contributions, but I don't think we have any direct knowledge of Marinus's work, but he comes up in Hapgood. What Hapgood says about this map regarding southern Sweden, they actually do suggest the remnant glaciers that covered this country at the end of the last ice age about 10,000 years ago. So comparing this map to the last one, Ptolemy to Zeno, he believes that the sources differed. Ptolemy from the end of the last ice age, Zeno may have originated much earlier. And the last map was the Hudi ibn Benzaram of Alexandria map, one of these portolanos, if you think of Nordenskjöld, so late 15th century. And Hapgood notes superior coastal detail, so he thinks this is close to that presumed normal portolano, maybe a direct copy. It turns out that here we learn that Hapgood also has an aunt who's an Eastern languages scholar and speaks Russian. And the aunt suggests that these faces are Coptic. So in these portolanos, stylistically, you'd have faces in the four corners and they'd be kind of cherub-like, and you see the breath coming out and they'd be representative of the four winds. So Hapgood looks at this and he says, geez, those don't look like all the other ones I see. His aunt says they look Coptic. So I think Coptic Christians, Egypt, and again, it's pointing back to the Library of Alexandria as a potential origin or source for this. So maybe that's where this came from as a copy of the original source map. One thing Hapgood notices, not only is this a very accurate map technically in terms of latitude and longitude, I mean, Straits of Gibraltar, boot of Italy, Sicily, Sardinia, Corsica. In some spots, they're showing some islands that don't show up on modern maps. And Hapgood interprets this in the context of all of his other discoveries as evidence of lower sea levels, because during the last ice age, so much water was caught up in the polar ice caps that sea levels were up to 100 meters lower. Okay, so Hapgood is an intelligent man, very versed in history. He understands the implications of what he's discovered. I mean, not only is it reinforcing the likelihood that the Earth crust displacement is correct, it's basically throwing history on its head in terms of long-term chronology and the fact that there was probably an advanced civilization in high antiquity. So he talks about some of the science and technology aspects of that. He talks about Hipparchus in the 2nd century BC, brilliant guy from my reading, who is attributed with the development or discovery of plane and spherical trigonometry. But obviously, he either rediscovered it or actually knew it, and is the first guy that his work made it through that we record. In terms of these kind of compass roses that you see on some of these ancient maps, they divide the circle into 12, and Hapgood feels that implies knowledge or a use of a 360-degree circle, 12 times 30. And he found that consistent with Babylonian or Chinese math and science. So the implication being that maybe these civilizations had, in terms of math and science, a legacy from this unknown civilization in high antiquity. And he also discussed the fact that he's seeing stuff that he shouldn't see geographically, geologically, and he links that to the possibility of Earth crust displacements. In his final chapter, because he also not only understands the science and technology history aspects, but sort of the broader implications, amongst the other things, he gives 4 principal conclusions of a vanished civilization. And you're almost seeing a despondent Hapgood at this point. He correctly says that the idea of a simple linear development of a society from Paleolithic to present must be abandoned. And he cites at least 20,000 years before present. So I think that's what Hapgood's thinking the last major Earth crust displacement happened. Every culture contains the seeds of his own destruction. And in this, he's bringing up the destruction of the Library of Alexandria in 3 acts, the firebombing of Dresden, and other great atrocities in the history of humanity. He talks about every civilization develops and uses a technology that contains the seeds of its own destruction. So he's anticipating possibly a nuclear holocaust, because he's writing in the middle 60s. And he actually crosses that line when he says the more advanced the culture, the more easily it will be destroyed and the less evidence will remain. And he asked the question, if New York City was destroyed in a thermonuclear holocaust, in eons or ages downstream, would an archaeologist be even able to recognize that a great city once stood there. So you can see that this process for Hapgood, even though he heroically followed the evidence where it led him without fear, it certainly had an impact on him. So I would like to end by giving a quote from Plato's Timaeus. I do this for the surreptitious reason that Matt and Cynthia won't think that I'm a complete intellectual Philistine and pretend that I'm actually knowledgeable. But I want to introduce the possibility that Plato is faithfully relating an actual conversation that occurred when the Egyptian priest said to Solon, there have been and there will be many and diverse destructions of mankind, of which the greatest are by fire and water, and lesser ones by countless other means. If this is actually true, any group in that time frame that would have had knowledge of a legacy civilization, legacy knowledge, would have probably been the Egyptian priesthood. So with that thought, thank you so much for presenting it. And if anyone has any questions or comments, I'm happy to go.
That was a great class, Stephen. Fantastic job.
Oh, thank you.
Yeah.
Yeah, that was really wonderful. One of the best classes ever.
Well, yeah, you threw so much out there. I didn't anticipate that. So thank you so much. And indeed, as Stephen just said, if people have any questions, as I mentioned in the chat box, put your name there. I'll put you in queue. So far, Martin was the first to slip in there. So Martin, I'm gonna give you the stage.